Hello and welcome back to Hilbert Spaces, the video series where we talk about inner product spaces and operators on them. And we are still talking about so-called orthonormal bases, and in today's part 15 we will talk about the existence of such an ONB. More precisely, we will show that every separable inner product space has an ONB. However, before we write down this proof, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, you can use the link in the description to download some additional material for the videos. So for example, I offer the PDF versions of the videos and quizzes and exercises. And then I would say, without further ado, let's immediately start talking about the orthogonal projection again. And there we have already learned, if we have a Hilbert space, so a complete inner product space, the existence of the orthogonal projection onto a closed subspace is guaranteed. So please remember that we need a Hilbert space and a closed subspace U. And then the result is that for each vector x in the Hilbert space, we have the orthogonal projection onto U. And this means that we have a unique decomposition where one part lies in U and the other one in the orthogonal complement of U. And now a nice result from Parseval's identity is that we can easily calculate this orthogonal projection if we have an ONB of U. And as usual, we denote these vectors by E alpha, and they form an ONS in X, but an ONB of U. Which simply means if we consider U as a Hilbert space, then Parseval's identity is satisfied in U. Hence, every vector U in U can be written as an infinite sum of the ONB. This formula is equivalent to Parseval's identity as we have discussed it in the last videos. And now, since this formula holds for every vector U in our subspace U, we can also use it for the orthogonal projection. Hence, the vector we consider now is x projected to U. Also for this one, this identity in U holds. Moreover, obviously, we can also just add the component in U perp as well. This one lies in the orthogonal complement of U, which means it will vanish when we put it in the inner product with E alpha. So nothing changes here, and we get a nice formula for our original vector x. We just have to calculate these inner products and form the whole sum to get our nice orthogonal projection onto U. And there you see, this is why ONBs are so nice. We can immediately use them to calculate orthogonal projections. And for this reason, you might already know that this combination here is known as a projection operator. More about these in the future, because first I want to guarantee that we can always find an ONB. And it turns out that most of the time we have a so-called separable space anyway. Therefore, I first show you the result about separable inner product spaces. For such nice spaces, we always find an ONB, and it's even countable. This simply means that the index set I here is a countable set. And the reason for that is simply because we have this separability here. And in fact, this term is not complicated at all. It even holds for metric spaces, where it says that we have a countable dense subset. And you know, for an inner product space, we have an induced norm, and with respect to this induced norm, we say that we have a dense subset. And now exactly this assumption we can use to form a countable ONB. So the only assumption we have here is that we have an inner product space X and a countable dense subset A. This means we can just write that the closure of A in X is equal to X. And here please recall, countable just means that the cardinality of A is not bigger than the cardinality of the natural numbers. Which also means that we can list the elements as x1, x2 and so on. And then we either get a finite set or a countable infinite set. And now I actually just want to look at a subset of A which is linearly independent. And indeed we can choose it maximal, which means we cannot extend it in A and still get a linearly independent set. And if we do that, then it should also be clear if we form the span of this set and take the closure, we still get the whole space X. And this makes everything much simpler because we just talk about a total set which is countable and linearly independent. And at this point you might already guess that we just have to do a Gram-Schmidt procedure to find our ONB. This just means that we can define step by step orthonormal vectors. Hence the first one, E1 here, should have length 1, which means we have to divide x1 by the norm of x1. And then we know that we can just form the orthogonal projection onto the direction given by E1. And now it makes sense to apply this to the next element in the list, which is x2. And obviously what we want here is a vector which is orthogonal to E1, so actually we want to have our normal component of this projection. So the formula tells us simply we have to take x2 and subtract the orthogonal projection. So this one is orthogonal to E1, and if we normalize it, we have our next orthonormal vector. Therefore also here, we just have to divide by the norm of this vector. So this is our E2, and now we can just continue inductively. And this is the reason why I've already written the sum, even in this case where we only have one entry anyway. So now in general we can define En plus 1 if we know all the other entries before. And then the only thing we have to show with this definition is that En plus 1 is orthogonal to all the other E vectors before. However, of course this one we already know by our orthogonal projection theorem. En plus 1 is essentially the numerator here, and this one is exactly the normal component. And the normal component lies in the orthogonal complement of the space that all the other E vectors span. Of course we can also calculate it, but we already know that this one is equal to 0. And by induction this holds for all k and all n, so indeed we have an orthonormal system. Hence this general Gram-Schmidt procedure we have seen here always gives us an ONS. However, what this formula here also tells us is that each vector xn plus 1 can be spanned by the E vectors as well. So simply said, we don't change the span at all with this procedure. However, by assumption we already know that the span of the x vectors lies dense in x. Hence the span of the ONS also lies dense in x, which means we have a total ONS. And there we know a total ONS is what we call an ONB. So you see, the separable spaces are nice because this whole Gram-Schmidt procedure works. Therefore, for these spaces we can always assume that we have a given ONB. Moreover, what we have seen here is that the ONB is countable, so the index set can be given by the natural numbers. And of course, in the case we have a finite dimensional space, this procedure can be just stopped at the dimension, and then we see we have a finite ONB for that. But obviously here the interesting cases are the infinite dimensional ones. So now, as you have seen, the result from above was for Hilbert spaces and inner product spaces, but we definitely needed the separability. If we want to drop this assumption, we can only say something about complete inner product spaces. However, there the result is quite nice, because no matter which Hilbert space you consider, you can always write down an ONB. And there, in general, we don't have a countable ONB. Actually, the proof here is not so different from the one above, but we have to extend our induction argument. Which just means that we have to use more from set theory, namely Zorn's lemma or the axiom of choice. However, for us this proof is not so important, because most of the time we deal with the separable Hilbert spaces anyway. Indeed, with the next videos I want to continue with the general projection operators. So really hope I meet you there again, and have a nice day. Bye bye.